proc_skip, which is this first method, which provably exhibits acceleration through local training, happens to be a special case of a new randomized version of the primal dual Daviesian splitting method, where the randomization is compression applied to the procs, and then the error caused by that compression is fixed with EF21. I have some other slides, but I don't have time to go through them because I want to start the last part here. I will only super quickly show you what I would normally talk about. I would talk about Ginger's work on fat procs if I had the time. Unfortunately, I have to skip it. But it's beautiful work, very impactful. And the reason why I would be mentioning it, because it clearly shows procs as playing a role in local training, just like in proc_skip. It's different, but it plays a role. And one can think of this as some sort of a parallel proximal point method applied to finite-sum problems. And it turns out if you think along these lines, we can also think through fixed point iterations. This was our work. I will completely omit this. But if you think along these lines of proximal point approach, then it turns out you can trace this back all the way to Nati's work with Oha, Chamir, and Tongzhang on Dane, and then Axerted Dane, and so on and so forth. And as you trace this line of work, then you end up at this paper of Sebastian again, where what was achieved was acceleration through local training, again, just like in proc_skip, but through a proximal point method point of view with some double stabilization, where what you get is not only acceleration through local training, but also through similarity. Just like similarity played a role in the Marina algorithm, and it led to speed up in presence of correlated compressors through these permutation compressors. Similarity plays a role in local training if the right algorithms are applied. And almost all of these algorithms on these two slides are of proximal point method type. This one is not. And you can see acceleration in distributed optimization under similarity. Similarity is mentioned in many of these titles. And the last paper in this line of work is this work where you have squared off, I believe, delta over mu number of communication rounds, where delta is the replacement for the smoothness constant, and is similarity constant, and mu is strong convexity. So for those of you interested in this line of work, these are the papers to be read. OK, now I have to, and I don't have time to mention all of this work. And I think this will be yours, right? Anyway, I just don't have the time. So I want to start with device heterogeneity. OK, so here we will work with the same formulation, but the KAUST model will be very different. So far in this first part, we ignored everything except for the communication. And even in the first part of the first part, we only thought about the worker to server communication as costing anything, and the server to workers communication costed nothing. Okay, just a quick recap. Then in the second part, we also focus on communication because local training is there to accelerate communication. And here we will ignore completely communication. We'll focus on something different. We will unignore it in the middle of the talk, but we ignore it at the beginning. So the KAUST model would be heterogeneity of the clients themselves. So let's imagine that client I, or worker I, takes tau I seconds to compute a stochastic gradient. So these are heterogeneous compute. The compute is heterogeneous. And let's say that these tau i's are ordered from the fastest to the slowest. And at the moment, think of these tau i's as being static, not changing in time. Some of the methods I'm going to talk about apply also to the setup where these times are possibly changing throughout the iterations, because workers may get busy with some other workloads and so on and so forth. There's additional heterogeneity of clients or devices, and that's communication costs. So not only we will not ignore communication costs at some point. At the beginning, we will. But once we unignore it, then not only the cost of communication will be there, but it will be different for every client. Because some clients might be able to communicate with the server with some very fast interconnect, I don't know, NVLink or whatever. And some other clients, this is slow internet, and so on and so forth. And these could also be changing in time in the future. So that's what we'll focus on. At the beginning, only this, and we'll assume that these thetas are going to be 0. And we'll work in the non-convex regime now, unlike in all of the previous parts, except for the Marina one. And we want to find an approximate stationary point. We'll have just two assumptions. One of them is Lipschitzness of the gradients of those individual functions. And then we have access to unbiased stochastic gradients with bounded variance. This is a very, very simple model, possibly the simplest model for variance. There are more complicated, more precise models, but we'll work with this model. And now the question is, what is the right SGD type method in this setup? If you just think about it, and we have abstracted away everything except now for the tau i's, okay? Imagine communication is infinitely fast now, and the only thing that costs is computation. What should we do? So here is one possibility. Server sends the model parameters to the workers. This takes 0 time because communication is infinitely fast. We're not worried about this. Everybody computes one stochastic gradient. Can compute more, but let's say 1. We're just coming up with some algorithm. And now this is the fastest one, right? So maybe this is 1 second, maybe this is 1 hour, and this is 1 day. Let's go really extreme, okay? And then this gets communicated to the server. This takes 0 time. Server averages stuff and takes SGD step with mini batch size 3. So what's wrong with this algorithm? I mean, obviously, it's not a good algorithm, but you tell me what's wrong. For example. So if this is really, really even slower than 1 day, maybe it's 10 years, let's say. I mean, we're thinking theoretically, right? So it could be in numbers. Then this guy probably shouldn't be in part of the training process, right? But it only makes sense if these functions are the same. If you have different stochastic gradients, but from the same function. If you are in the data homogeneous regime, it's possible to remove the slow worker if it's too slow, because it doesn't have any data that others don't have. Right? So this would not be a good algorithm if tau 3 is really, really large. So let's say it's not very large, it's just a day. Maybe a day is not that large, maybe. I mean, who knows, right? Or maybe it's just 1 hour. So this is second, 10 minutes, 1 hour. Maybe it's OK to use it. But what is then the problem with the algorithm? What can we do better? I know it's easy what I'm asking, but let's just have some discussion.
We could use the faster workers more when this worker is slowly computing it stochastically.
Yeah. So for instance, and that's some sort of weird type of local training, if you think about it. Like we give it more work, okay? But it's not local training, it'd be computation of more stochastic gradients. It's local work, but we're not updating the model. So maybe we set a budget. So this is hour. So this is 10 minutes. This is 1 minute or whatever. So we just collect stochastic gradient for an hour. So this one gives us many more stochastic gradients. This is fewer. This is just 1. And then we communicate. That sounds already like a better algorithm. And that makes a lot of sense if these functions are the same in the data homogeneous regime. So let's worry about the data homogeneous regime first. OK. But is it the best algorithm? Maybe there's even better algorithm. So it's kind of, this is what I want to ask, right?
The homogeneous setting, I'll just implement hog-wide. Like,
Right, you could do asynchronous SGD. You could do asynchronous SGD, and I'll mention that too. Hogwild will have an issue though. And the issue is, what if this tau3 is 1 year? Hogwild will not ignore that guy. It will train for a year, and after a year, it will update the model, which already was updated for a year, with this very stale stochastic gradient computer at the beginning. And that's a problem. That's already a problem. So we have three sources of heterogeneity here in this setup. It's the data, and you already see how the data heterogeneity somehow is relevant to this compute heterogeneity. Because if this tau3 or whatever was very large, then we could ignore if data is homogeneous, but if data is heterogeneous, we cannot ignore even the slow worker because it contains part of the problem description, right? So, and we're ignoring communication now is infinitely fast for now. It will not be later on. Okay, so let's start with some approaches. So it turns out that there is this solution, engineering solution used in practice, and it's let's use asynchronous updates. And in federated learning, there are at least these two papers and more, FedBav and Papaya, which introduce some level of asynchronicity. Let's not go into what exactly is being done there, but asynchronicity is relevant in federated learning as well, clearly. And we can talk about Hogwild, as you mentioned. So this dates back to 2011. So I was there in Budapest when this was presented. In fact, I was invited to be co-author of the paper, and I was stupid and said no. I should have said yes. After they already wrote this, they were then writing journal version, and I had some kind of improvements of the proof and so on, and I was young and stupid, and I said no, it's too bad. Anyway, this is a beautiful paper, won NeurIPS Test of Time Award, very influential paper. Okay, so this was the motivation for our work, and this is Anastasia's work, and Sebastian and Martin's, again, from June 16 and June 15, which is basically the same day. There's another team of Konstantin Mishenka, my former PhD student, Francis Bach Blake, and Matthew Even. So this was his postdoc in Francis' group. And they kind of done the same thing. Not exactly, but let's say the same thing. And what they've done is that they've analyzed asynchronous SGD in a nice way, different from the ways this was analyzed before, where typically what the way people analyze asynchronous SGD before is that they assumed the delays are first-order citizens. The staleness is first-order important thing, and that's input to the problem description. And then you try to bound away the effect of staleness. But here, it was done differently, and you could really see what's going on with this asynchronicity. So we read these papers, very, very nice papers. Everybody should start with them. And with these people in my lab, we asked, what can we do? Is this the end of the story? And I will describe what these papers do. And we realized, no, that it can be further improved, whatever they've done. And again, I will explain what they've done. And then we realized that our improvements cannot be improved anymore. So we obtain optimal algorithms, in optimal asynchronous algorithms in some sense. So I will explain all of this. And it started with this one 2 years ago, and then we wrote more and more papers and so on. And I will explain what they are. So this one, here we assumed that the data is homogeneous, and the computation is arbitrarily heterogeneous. And we propose a new KAUST model, which we call time complexity. And time complexity is just what you would normally think. It's the amount of time it takes to solve the problem, to find an approximate stationary point. It's not the number of iterations, because for these asynchronous type methods or parallel methods, number of iterations doesn't make any sense. But time makes sense. And once you come up with this notion of time complexity, you can prove some lower bounds. And then you can prove some upper bounds. And the upper bounds proven in these papers of Anastasia and Konstantin were not quite tight. They didn't match the lower bounds that we proved. But a simple trick made these bounds to be equal. So we just came up with a simple trick and with the lower bounds. So that's the Rennala SGD algorithm. So this is an optimal algorithm in terms of this new notion of time complexity. Malenia SGD is also optimal, but that is optimal under data heterogeneity, arbitrary data heterogeneity. So that method cannot ignore any workers. Rennala SGD can ignore some slow workers. And it will. And it will be optimal if some taus are very large to just ignore those workers. And this is what those asynchronous SGD methods before didn't quite do. They didn't ignore some workers, and it was important to ignore some workers. OK, then in Shadowheart SGD, we complicated or improved or tightened or whatever you want to call it, the KAUST model. And we asked the following question: what happens if communication also plays a role? So now you have arbitrary communication heterogeneity, arbitrary computation heterogeneity, but you have data homogeneity. You couldn't figure out how to deal with data heterogeneity. So we have two levels of heterogeneity there. And we could also design an optimal method. We proved the lower bound and an optimal method, and we call it Shadowheart SGD. Interestingly, this method uses compression. Okay, so it has some aspects of Rennala SGD, but also uses compression. Then in this work, we ask similar questions, but for finite-sum problems, not expectation problems. And for finite-sum problems, we can do variance reduction. Just like you have seen, let's say, Diana does variance reduction for DCGD, or something like SVRG does variance reduction for SGD, and so on. So you can do variance reduction in finite-sum problems, and the upper bound can be improved, and the lower bound can be improved, and we designed this optimal method, which we call Freya-Page. So this is unimprovable in the case where each client contains at least as many data points, training data points, or functions, as is the square of the number of clients. So in that regime, we have an optimal method. Then we're able to generalize all of this on arbitrary connected networks, where the communication pattern is dictated by links between nodes. And we just kept going. And so this is a beautiful paper by Sasha Churin after he left my lab. And maybe I would highlight this work. I don't want to talk about every single one. So this method is the first asynchronous SGD with optimal time complexity for homogeneous data. Because it turns out Rennala is optimal in terms of time complexity, but it turns out to be semi-asynchronous, not fully asynchronous. It uses synchronous updates, and I will explain that, and asynchronous stochastic gradient collection mechanism. So it doesn't asynchronously update the models. But Ringmaster SGD does. And it also has optimal time complexity. And then we also wrote Ringleader, which does the same thing, but for heterogeneous data. So that's the first optimal asynchronous SGD for heterogeneous data. OK, and it turns out that some versions of local SGD also have optimal time complexity, but not the original one, but something they call dual local SGD or decaying local SGD under data homogeneity now. So these things are all connected. Now you may ask, where are these names coming from? Where those names come from? They come from games because Sasha Churin saw these games somewhere. No, he's actually playing those games. OK, so this is the summary of some of those papers, just like I had summary before. And as you can see, almost everywhere we look at the smooth non-convex regime. You may ask, why? Why before we looked at the strongly convex regime mostly in the previous lectures and now smooth non-convex? Because if you want to have optimal methods in the convex regime or strongly convex regime, you need to use momentum, Nestor of momentum. And that turns out to be a complicated tool. So in the smooth non-convex regime, it's easier to obtain optimal methods because you don't need momentum. So in fact, we have a larger class of problems, but it's easy to prove optimality. OK. So it's some sort of, it's not cheating, but it's simplifying our life. But we also have convex case here. Almost everywhere, we minimize expectation. In this one paper, it's a finite sum. Then we can use variance reduction. Everywhere we have just centralized setup, which means there's one hub and many clients. But in this work, we also work on a network. Here you can see we have compute heterogeneity everywhere. That's the common thread of all of these works. Arbitrary compute heterogeneity. These compute times are arbitrary. And communication is infinitely fast everywhere except for these papers where we consider also communication cost on top of it. So this is a more precise cost model. And we wouldn't be able to come up with optimal methods here if we didn't have optimal methods in the simpler cost models. So these cost models, making them more and more complicated, also makes it tractable to solve these problems in the first place. Okay, and data heterogeneity, mostly we don't have, but in some cases we do. All right, so let's discover the algorithm together through a picture, the Rennala SGD. So we start with 4 clients. There's a watch, phone, laptop, workstation. And this would be data homogeneous regime. So all the clients can solve the problem on their own. They have the same function. So hero SGD is this idea when you have a really amazing person on your team, you go on vacation and ask the person to solve the problem. That's the idea. That's hero SGD. That's the hero. This guy is the hero, and everybody else is relaxing. It's very fast because it takes just, let's say, 1 second for it to compute one stochastic gradient. So it just keeps going. And updates, you get updates of the model like this, and nobody else is doing anything. Everybody else is slower. That's hero SGD. I mean, this method makes a lot of sense sometimes. When the hero is so fast, so much faster than everybody else, that it doesn't make sense for anybody else to contribute. This might be an optimal method. Let's just imagine that the other taus are 10 million years. Obviously, this is the optimal method, right? So sometimes this method will be optimal from time complexity point of view, intuitively speaking. And it's true, we can prove it. OK, but sometimes not. So sometimes this idea is good. Let's call it naive mini-batch SGD. So now everybody works, and we want to be fair to everybody, so we give one job to everybody, which means compute one stochastic gradient. But now, this guy is fast, this guy 2.5 seconds, 3.5 seconds, 8 seconds. So now we do one mini-batch SGD step, and we repeat this pattern, and this is the method. This is just a very simple version of mini-batch SGD. Now, this would make a lot of sense if these times are roughly the same, because there's not much idle time, and might even be optimal in some regime. But it doesn't look like it's optimal here, because there's too much idleness. Okay? But there will be a regime where this is optimal. It might be optimal in some regime. Intuitively, you can feel it that it could be the case, right? Depends on the tau-ice. OK, what is asynchronous SGD? Well, the idea is not to have so much idleness. So let's not have any idleness. So asynchronous SGD just follows this algorithmic idea that everybody is a slave, which means nobody has rest ever. Okay? It's just this intuition that if everybody always works, maybe that's the best way to squeeze out the juice of these workers. I mean, that might be wrong, but if you follow that intuitive idea, you don't allow any idle time. So that's one part of the recipe. The other part is everybody is useful, which means we'll not ignore anybody's work. We'll use everybody's work, which already you can feel it's problematic if, let's say, this guy was super, super slow. After 1 year, it gives you update, because you're forced to use that super stale update after 1 year. So that's problematic. So this is how the method would work. If you just keep staring at it and you never see an asynchronous SGD, you see that this is a very strange algorithm. Right? So there's no idleness ever. And at every time that somebody finishes computing stochastic gradient, it uses that stochastic gradient to update that current model. Okay? And at that moment, it reads the model parameters, computes new stochastic gradient at those model parameters, and keeps computing and updates and so on. So I'll show it again if you haven't seen this before. So this is how it works. Just keep updating, and these colors correspond to when this stochastic gradient was computed. And this pattern gets repeated. Okay? And this method also could sometimes be optimal, actually. So that's the problem, that all of these methods feel like they might be right in some setups. So what's really going on? Well, this was the inspiration, as I mentioned, and they've done almost all our work. So basically, these papers almost solved the problem, but didn't notice just one little detail, which is you should kill some of the slow workers. Like you don't take updates also from the slowest workers. If you add that one requirement, you get optimal time complexity. So that's what Rennala SGD is, and it works like this. So that's this first method from the first paper. And what Rennala SGD does, it is mini-batch SGD. It is nothing else than mini-batch SGD, but with the magical mini-batch size. And the mini-batch size, let's say, will be 11. I'm just making this up, OK? And this mini-batch size does not depend at all on these times, at all. It's nothing to do with the compute times. It only depends on the accuracy that you want to achieve on your epsilon, OK, for the stationary point, and on the variance of the stochastic gradients, just on these two parameters. It's some sort of ratio of the two, really, OK? So the mini-batch should be computed that way. And then the algorithm just says this. Let everybody compute stochastic gradient at x0, and one after another, and send it to the server immediately. And the server is waiting for the mini-batch size. As soon as it gets the mini-batch size 11, it says stop, and takes mini-batch SGD step, and the process is repeated. That's what the method is. OK? And in this case, the mini-batch size 11 means that we get it after 7 seconds, but 7 seconds is less than 8 seconds, which was the time it takes for the last worker to compute one stochastic gradient. And that's why that worker is ignored. We don't need that worker's input. And you get worse time complexity if we did. This is what Rennala SGD is. OK? So we have an upper bound. And the upper bound is basically 100 times, let's forget the 100. We don't like the 100. Times certain expression. And the expression is implicit because you have to solve a minimization problem over some parameter m that doesn't show up in the algorithm. And n is the number of workers. And the m appears in 3 places. And the optimal m might be anything between 1 and n. And the way you should think of it is this. If the optimal m will be 1, then you get hero SGD as a special case. The only one worker should work. If the optimal m is n, then everybody should work. So this m implicitly will tell you how many of these workers should work. Now, here we have harmonic mean of those compute times and some other expression. So what Anastasia showed in her paper was basically got this complexity, but with m is equal to n. If you just plug in m is equal to n, that's exactly what they proved. Can you confirm that's the case? Yes, OK. So good. So this must be better because we optimize, we have other choices. So we cannot make it worse if you had other choices, right? So that's an upper bound. But it turns out that this, we have a matching lower bound. So this cannot be improved. These are the Lipschitz constant. This is initial suboptimality. This is the variance bound. This is the accuracy level. OK, so that's what it is. Now we have a matching lower bound, and we know because I copy-pasted the same expression, so it must be the same. But it's interesting that such a strange expression turns out to be lower bound. So this is an optimal parallel SGD method. Now, it's optimal with respect to time complexity. And time complexity is something new, which we had to define in the paper, because normally people count iterations. And I was telling you we shouldn't be counting iterations in parallel methods, because that's not a good notion of time. So instead of this classical Oracle protocol, where you have some function and some Oracle distribution, an algorithm, and so on and so forth, I don't want to go through the details of this. Which counts this inf sub inf, okay, the number of iterations it takes to solve the problem, basically. We have to say, no, this is not good for parallel methods, because number of iterations doesn't correspond to time. It just doesn't correlate with time. However, if you introduce into the oracle notion of time, so that the oracle remembers what times it is, then you can introduce a new notion of complexity, time complexity, where you do the same thing, this inf sub inf, but now over time, not over iterations, over time it takes to solve the problem. And so that's the difference. And it is natural for parallel methods, and the upper bound and lower bound are the same. So asynchronous SGD, as you can see, that's precisely the same expression. You just plug in m is equal to n here. So this is what these authors proved. And if you look at mini-batch SGD, that's definitely worse. Asynchronous SGD improves on mini-batch SGD because this expression is the same, but instead of the maximum tau, you get the harmonic mean. Harmonic mean is better than maximum, always, right? So this is improvement on this, and this is improvement on this, and this is not improvable anymore. OK, but remember, this is the homogeneous data regime, which is not super practical. So basically, you have the setup where everybody can solve the problem on their own, but the question is, will some collaboration be helpful or not for them to solve the problem faster? And sometimes, yes, sometimes no. Hero SGD could be the problem. Mini-batch SGD with special mini-batch size, and so on could be the problem. Now, you can play with some toy experiments where we choose the compute times to be square root of I for 10,000 computers. So this is just artificial toy experiment. But everything is done according to theory. So this is really Lipschitz, non-smooth, and so on and so forth. And you can see that Rennala SGD can be order or even 2 orders of magnitude faster than asynchronous SGD, and mini-batch SGD doesn't even show up here on this plot. OK. So now we have some extension. First extension is what happens if you want to design an algorithm which is optimal, but now the data can be heterogeneous. Well, the very first thing that you realize is, as I said, we cannot ignore any worker anymore. It's impossible. So I won't go through the details of the algorithm, but this loop condition ensures that you get at least one stochastic gradient from every worker. And once you get it, you stop. So that's really how this works. You wait, and then you stop. And then you reweight because you want to have unbiasedness. So you divide the aggregate stochastic gradient that you get from worker I by the mini-batch size that you got from the worker I, and you average those things, or add up those things. Now, the effective mini-batch will not be just sigma square of epsilon, as for Rennala, but the max of this and n. And it turns out that this very simple modification to Rennala, which we wouldn't think of if we didn't develop Rennala in the first place, is optimal in the compute heterogeneous and data heterogeneous regime. Now, communication is infinitely fast in this KAUST model. So the upper bound for Malenia SGD is this. No longer any harmonic means around. We have arithmetic mean in this stochastic term, and the maximum of those compute times in this deterministic term. The lower bound has the same form. Mini-batch SGD replaces this arithmetic mean by the maximum. That's why it's worse. OK. So that's what we now have for this better, well, the same KAUST model, but under yet another level of heterogeneity, data heterogeneity. OK, now we can handle the convex regime, but I will skip it. I don't want to talk about the convex regime. So let's now think about adding communication into this. Now, Shadowheart SGD is optimal under arbitrary compute heterogeneity and communication heterogeneity, but under data homogeneity. We don't know how to do it under data homogeneity. So if you can do it this semester, hopefully somebody will do it. Let me know. It'd be great to see that. I have one slide where I explain what Shadowheart SGD is. It turns out to be easily explainable algorithm. So this is it. This is the algorithm. It has this one synchronous update. So think of this as an SGD, where this is the stochastic gradient estimator. But it has very strange structure. As you see, it includes some compression. So it's good that we talk about compression, because compression is important here. So let's think about what's going on. So gamma is going to be step size just 1 over L, basically, where L is the smoothness constant. And there's this notion of equilibrium time, which depends on all of these quantities. It depends on the compute time, on the communication times, on the variance, accuracy, and on variance of the omega of the compressors. Imagine that you are able to compute this equilibrium time. You just need to solve one equation in one variable whose unique root is this t star, and it depends on these quantities. We don't have an explicit formula for it, but you can quickly find this if you want it with some root finding algorithm. So once you have this equilibrium time, this magic time, let's say we have it. Let's say we don't worry about how we compute it, we have it. If you have it, then you divide this equilibrium time by tau I, and this tells us how many stochastic gradients should worker I compute before it does any communication. So what does this mean? So let's say the tau I is very small. What does that mean? That the worker is very fast. If the work is very fast, then tau star divided by tau I will be very large. So bi will be large, which means that the worker will compute a lot of stochastic gradients before communicating. In Rennala, we didn't worry about communication. Why? Because it was infinitely fast. So every time we compute stochastic gradient, we'd send it to the server. It didn't matter. But now it matters. Okay, now it matters. We cannot anymore just send anything. So faster workers compute more stochastic gradients. They buffer them, add them up, and then this gets sent. But it gets sent only after the sum gets compressed. And it gets compressed with unbiased compressor with this conic variance. Think of rand1 compressor, for example. Now what happens is that this process gets repeated mi times. So again, bi stochastic gradient, sum up, compressed again, mi times. What is mi? Mi is the equilibrium time, but now divided by the communication speed. So if theta I is very small, that means the worker can communicate very quickly. That means we can afford to send more compressed messages, right? Because the communication is fast. We can send more of them, right? There won't be any imbalance. And then the end of it is just do some weighted averaging of all of it to get unbiasedness, and the weights have a very specific formula. Let's not go into the formula. And now it turns out that this algorithm has optimal time complexity. There's a lower bound and there's upper bound, and they match. However, we are no longer able to have an explicit formula for the lower bound. We have an implicit formula, but we still know that the implicit formula for the upper bound and the lower bound are identical. So we know we have optimal time complexity. And in order to give some sort of an insight into what's going on, we can compare to QSGD, which is basically distributed compressed gradient descent, or Rennala SGD, or asynchronous SGD. We can throw in the time complexity, which is just the equilibrium time multiplied by L over epsilon. And we can think of some scenarios. So what happens if sigma squared over epsilon, which is the ratio of the variance and the accuracy tolerance, is 1,000 or million? Well, we set Shadowheart as the baseline, and we want to see how much slower the other algorithms would be in theory if we plug in these numbers into the theoretical complexities. So this would be 10 times worse. So Rennala SGD and asynchronous SGD in this case would be 10 times worse. In this case, 100 times worse. In this case, 50 times worse. This would be 10,000 times worse. This would be 100 times worse, 3 times worse, and so on. So you can see that all of these methods are worse by sometimes even 4 degrees of magnitude, or 2 degrees of magnitude, 1 degree, or just 50%, but they're always worse. So in any of those regimes, Shadowheart SGD does better. So this is somehow how we can compare the complexities, because this T star is implicit root finding thing, and we cannot compare it to these explicit expressions. OK. So you can run this, again, in some simulated environment when you set these communication times to be square root of I over D, or over square root of D, or D to the power of 3 over 4, just to have some varying degrees of communication speed. And you will see that consistently the green line, which is Shadowheart, is near or at the bottom. So whatever the setup is, you get optimal performance in actual time. And sometimes some of these other methods do quite well. So I don't know, in this case, SGD does pretty well. And there's SGD hero, the blue one. In this case, asynchronous SGD does really well, and mini-batch SGD does really well. But the whole point is that in some regimes, these methods are not optimal, but Shadowheart is always optimal. OK, if you add more workers, you can have even larger differences. All right, so Freya is the optimal method if you have a finite-sum structure, because then you can do variance reduction. And I will not go through it. Again, it's optimal. And the variance reduction mechanism looks like just the one we have seen in Malenia, right? But instead of compressing the gradient differences, we subsample gradient differences. Okay? So here, variance reduction is important to get the optimal time complexity. OK, I will not go into the details here. This is just a very high-level description of Freya. Again, we run some simulations. And again, Freya does best among all of these other methods in the simulated toy experiments. OK, good. Amelie is the method which works on a network. And now we have everything is heterogeneous. Communication, computation, and data. And we have an optimal method there, too. Again, all the expressions are implicit. That's the end. But I wanted to say something. What was that? OK, before I say that, maybe any questions? I went through this without talking to you. So, yes?
So my first question is, when you compare the rates, you say that, let's say, Rennala SGD or QSGD is like 100 times or 10 or 1,000 times slower.
Right.
So do you compare it with omitting the constants that are coming from analysis? Like, I mean, constants that are not parameter of the models?
No, in this case, we plug in constants for everything, for L and for everything.
Yeah, but like there is also, like, remember you said you had some constant that
like 96?
Yeah. Do you count that?
The honest answer is I don't remember. If we don't, that would be bad. I need to double check. I hope we do, because otherwise it would make sense. So I would say almost sure that we do, but I don't remember.
And another question is, when you assume like experiments that you do for asynchronous time,
yes,
it's like square root of I. It looks like the devices are very diverse in terms of time.
Yeah.
Like,
it's not the worst case. It was just some sort of heuristic way of throwing in diversity.
Yeah.
Because under this heterogeneity, you can see differences. If you have very homogeneous setup, then many methods will work well. It's the heterogeneity and extreme levels of heterogeneity that cause issues.
Yeah. Do you think like what would be the reasonable like model of the, like what would be application of this? Let's say if you have chipboard or like some other things. What would be, or if you have like a lot of devices and you want to train a large model, what would be the realistic QI for different devices? What would be the realistic model of the time?
So one answer is that I don't care, because we get the optimality under absolutely any of these numbers. And not only that, also if they vary in time. So I didn't show those results, but Rennala SGD will work. The method works without knowledge of those times. Why? Because you need this mini-batch, this magical mini-batch size 11, which is just sigma square over epsilon. It has nothing to do with the tau i's. You wait for the mini-batch size, whatever the tau i's are. So if a worker suddenly becomes slow, you don't care. You just say, OK, I'm not going to get anything from you. You wait until you get 11 stochastic gradients. So if, let's say, everybody fails, except for one worker in the data homogeneous regime, you get all 11 stochastic gradients from that worker. And that's your iteration. That's what Rennala SGD does. So Rennala SGD is robust to even changes of those compute times. And we can prove optimality even under arbitrary compute times dynamic. We have a formulation for what we mean by arbitrary computation dynamic. And we have optimality even under that. So it's completely robust to all kinds of failures of these nodes and so on and so forth. But of course, that's only the case for the Rennala. There's the data homogeneous regime.
So it does not, but in one of the methods you have this T star, right? So which depends
Yes.
on the parameters.
Yes.
It's a different method, right?
That's a different method. That's
But
the shadow.
Rennala is like agnostic basically to all the parameters, right? In terms of the time.
To all the taui's, yes.
Okay.
But Shadowheart is not, because the T star influences the two parameters, which is how many stochastic gradients you have to buffer, and then how many times you repeat it. That depends on the equilibrium time. So in principle, you have this hyperparameter, which let's say you don't even know what it should be, and then you have hyperparameter, you have to search for it.
Okay, okay.
Like that would be the kind of practical approach. So this is just a proof of concept that such a thing exists. No free lunch. Any other questions? Okay, so let's see. There should be one thing that I wanted to say, but I didn't. Let's see whether it's there or not. Right, so what I wanted to say is this. Now, all of those methods that I mentioned, Rennala, Shadowheart, they're all synchronous, right? There's always synchronous update, which tells you that this idea of asynchronicity was just an intuitive idea, engineering kind of intuition that might be the thing that handles device heterogeneity, but it's not true, because we have optimal time complexity without asynchronicity. That tells us that asynchronicity, the hog wild type of asynchronicity, was too wild. It was too much of an asynchronicity that will not give us the optimal time complexity. However, that doesn't mean if you have a synchronous method, which is optimal time complexity, doesn't mean that an asynchronous method will not have optimal time complexity. It's just not hog wild, right? And it's not the standard asynchronous SGD. However, Ringmaster SGD is an asynchronous method with optimal time complexity. What does it do? It's just Anastasia's method, but with just buffer on how much staleness you allow. So there's a parameter, R, which tells you don't accept older stochastic gradient than 5 or 10 or whatever, so some number. Whatever is within the buffer of staleness, apply. What is not, don't apply at all. This kind of 0-1 rule. And that buffer R also depends only on sigma star and epsilon, sigma square and epsilon, and not on the times at all. So this is something like in your work, you have these varying step sizes that try to kill these stochastic gradients, and you kind of may decay them. So basically here, the story is that the decay should be 0-1. It should be either accept fully or don't accept at all. And that's a very simple mechanism leads to an optimal method. So there is an even simpler method than Ringmaster SGD, which is going to be optimal, and you can read about it in the Ringmaster SGD as kind of intuition, which is nothing else than, let's look at Rennala SGD. Where is Rennala? So you have Rennala SGD, right? And this one takeaway message from this is that we shouldn't use the watch, the slowest worker. Once we know that we shouldn't use the watch, that we should use these 3 workers only, we don't have to do mini-batch SGD. We can do asynchronous SGD of Anastasia on those 3 workers. So if you know the taui's, you can, in principle, solve the minimization problem over M, figure out how many workers should work, which are the slowest one, which should not work, kill them, and do asynchronous SGD on these 3 workers. And that will have optimal time complexity. But for that method, you need to know the taui's. There's a problem, but it will have optimal time complexity. For Ringmaster SGD, you don't need to know the taui's because you have a buffer on the staleness of the stochastic gradients, and that's enough. And the buffer has nothing to do with the taui's. It only depends on sigma and epsilon. So that's the beauty of Ringmaster. And another beauty of Ringmaster is that The buffer doesn't depend, since it doesn't depend on tau-ice, it doesn't depend on whether these workers drop out, get dead, or whatever. That doesn't matter. Even if all of them die and one survives, then this thing will be hero SGD and it will be optimal with respect to that particular dynamics. So that's what ringmaster SGD is. That's truly asynchronous. And if you look at the experiments, they improve on the Rennala SGD behavior. But of course, you cannot have more optimal method than an optimal. So the improvement is in some kind of constants, like maybe 20%, 30%. But it matters in practice. In practice, you get 1%, 2% improvement, maybe savings of a lot of money. So that's important. The asynchronicity is important, but not because it solves the device heterogeneity problem, but because it squeezes out a few constants out of whatever idleness remains. And what is this last method? This ring leader, that will be the last thing that I want to comment on. Ring leader. So that's the latest one, which we wrote in September, just got accepted to iClear. So that's asynchronous, but now under data heterogeneity. So just like Malenia was optimal for data heterogeneity, but was synchronous, and Rennala was optimal under data homogeneity, but was synchronous, ring leader is the asynchronous version of Malenia. But it's a much more complicated method, and it has some saga-like components. It's not an easy method. It's a very difficult method. It took us quite a bit of time to figure that out. And yeah, anyway, I'll stop here. Thank you very much. Happy to answer any remaining questions.
I had one really quick high-level question. So covered a bunch of different areas. First of all, thank you, because there's a ton of work to cover here. So I appreciate you pulling out all of these salient points about federated optimization. You talked about work in communication, local training, and heterogeneity. I was curious, like looking forward, which of these areas or all of them, are there places where you think they're the most exciting sort of open problems to be tackling?
Well, to me, all of them are equally interesting. And the way I'm thinking of all of this is, let's think about more accurate models, cost models. And they may be inspired by current industrial practice, but I'm quite happy to think about cost models which are forward-looking, where maybe in 100 years, 50 years, 10 years, we'll be working with very different computers, and then these other cost models and other algorithms might be relevant. So I don't want to just think about whatever is being done now, because lots of the take-home messages from these kinds of work apply equally to now this cross data center training. So that fits into this framework very well. It's not classical federated learning or federated optimization, but if we redefine federated optimization as distributed optimization where everything can be heterogeneous and difficult and whatnot, then it's completely fine, because you can play with the communication costs. Now inside data center, you would have super fast NV links or whatever. You can put that into those data eyes between. You can have slow links. So it's just a different cost model, and you would then try to design optimizers for that. Now, there's lots of unknown. So as you've seen here, for this device heterogeneity stuff, for these asynchronous methods, almost none of this is touching on the convex case. All of this is non-convex case. And we may think, okay, that's fine. But in practice, these models are not only non-convex, but also non-smooth. This is all smooth. We don't know anything about the non-smooth case. Another problem is that even if you solve the non-smooth, non-convex problem, even that is not going to be good, because in practice, the optimizers that work best, such as Muon and Adam and MW, they were designed for the non-smooth convex case. So that seems to be more relevant, even though these neural networks are not non-smooth and convex. They probably approximately are, and we don't know how. So that's completely open. We don't know anything about that. So I want you to think about all of these as some sort of models, toy models, which work very well if you have a problem that satisfies exactly those assumptions. When you do, you see the effect. When you cook up a problem which is L-smooth and non-convex and satisfy these theoretical assumptions, all of this has predictive power. So it's not toy from that sense. It's toy from the sense that these assumptions are not satisfied for these large language models and neural networks and so on. That's the problem. But we don't know what assumptions are satisfied. Nobody knows that. These are engineering constructs with no nice mathematical properties. So we need to put a lot of work into trying to figure out what those properties are so that we can come up with new classes and so on and so forth. But going back to your question, I think local training clearly is important and is relevant even when you think about compression, because let's say compression error feedback of procs gives us local training, but there are more of these connections. For instance, compression could also lead to partial participation, because if you compress and you have this Bernoulli compressor, where the compressor is identity with some probability and 0 with some other probability, that basically induces client selection. So it seems that compression can explain local training, and it can explain also subsampling. And these things appear in federated averaging. And that's why I also started with compression, because I think that's the most fundamental idea here. It's compression. And when you apply to procs, you get local training. When you apply specific procs, you get subsampling. We're just scratching the surface, I think. Yes?
So you presented this dichotomy for the asynchronous part of the talk, where in the homogeneous setting we sort of see that you don't benefit from asynchrony because you can kind of fix the batch size.
You want to have something in between,
yeah,
right?
that is intuitive.
Yes.
In the completely heterogeneous setting, I'm assuming the lower bounds are relying on this chain function or Karman type construction where you force dependencies on machines so that you have to really wait for them to come and then use their update, and that's why somehow maybe synchrony is useful. But again, the
we want something in between.
I'm just saying in between might be interesting because this is precisely where asynchrony might be useful.
Absolutely.
And we've seen this before in this literature, right? Like even for localisticity, homogeneous setting.
Yeah. This is the same thing as similarity. The notion of similarity captures exactly this for local training, because similarity interpolates between arbitrary non-similarity, because the similarity coefficient is upper bounded by the smoothness constant.
Yeah.
And that's arbitrary non-similarity, right? And if it's 0, you get perfect similarity.
Yeah.
And in the same sense, you may have some degree of homogeneity, and you would expect that some better algorithms could be designed for that in-between phase, but we know nothing about it. There's no result. But it's definitely an interesting thing to think about it. We thought about it a little bit with Arto. We didn't succeed. Not much, a little bit. It doesn't seem to be easy. Maybe it's tricky.
The lower bound itself might be, possible to weaken it. It is possible to weaken it in general using the second.
Yeah, but even the upper bound, just because once, because you see here the whole trick to get a better time complexity in the homogeneous regime is that these slow workers, you can just kill them, right? But in the heterogeneous, you cannot, because then you cannot solve the problem. And this is a binary thing. So there must be some sort of a thing which says if you ignore a worker, you can still solve the problem approximately, and the notion of optimality should be some sort of approximate optimality. And we don't have these kinds of things yet, so that has to be thought through.
I think we need an asynchronous homogeneous analysis to be able to interpolate, which is optimal to be able to interpolate.
I don't understand. What do you mean, asynchronous homogeneous? We have an asynchronous homogeneous analysis.
Which
There's the ringmaster.
Kill the, actually.
There's the ringmaster analysis.
But you mentioned it's synchronous in the sense that you still make like a...
Ringmaster is asynchronous. The Rennala is synchronous.
Rennala is synchronous,
Yes.
but the Rennala is the optimal one in the homogeneous setting.
Yes, and ringmaster too. But Rennala is synchronous, and ringmaster is asynchronous.
So is there an asynchronous method in the homogeneous setting which is also optimal?
Yeah, that's ringmaster.
Oh, that's ringmaster. Oh.
Yes. That's the one where you have the buffer of staleness.
Okay, yeah. Confusing too many algorithms, but
Yeah.
makes sense.
Apologize.
Yeah.
Yes.
You mentioned kind of like discussing their predictive power and application to like deep learning problems. And I think just kind of like surveying what is the cutting edge right now, why SGD works really well for like deep learning is about the implicit bias of SGD algorithms. So what that means is that different variants of SGD, they might all find an interpolating solution for the training set, but not all of those interpolating solutions are good population functions. So the problem with that literature is that it's a very specific analysis for every different variant of SGD. So if you start using like Freya or these your what's it called?
Shadowheart.
Like each of those would need a different analysis under this implicit bias kind of framework. So I think there needs to be some kind of combination of simply finding an interpolating solution quickly does not always give you a good population predictor. And that's kind of like what is under discussion right now in the deep learning literature, and how does that relate to these really fast kind of time optimal optimizers?
Well, what you touch on is the intersection of everything I talk about and generalization, right? That's what you touch on generally, right? Yeah. And the honest answer is nobody really knows in this deep learning what drives the generalization. For convex models, we know a lot, right? For linear models.
Well,
but in this deep learning,
it's being developed now.
I know, but I'm not convinced by anything I have seen. So people try to say flat, minima, and implicit biases, all kinds of explanations. To me, they're not really very convincing. I don't think we know really what's going on. However, if you think about it, it's a Rennala. Rennala minimizes expectation. But you get fresh samples. This is not empirical risk minimization problem. You have a fresh sample every time. That's actually the generalization problem. You will have the best generalization error because you minimize the expectation. So in some sense, it's no problem, right? Now we know that even if you had a good generalization, doesn't mean you have a good predictor, right? Because you can have a fundamentally problematic prediction task if it's a prediction task, and even good generalization doesn't mean much. So I don't know. So that complicates things even further, asking about generalization here. Yep, so I don't really have any good answers. This is purely optimization point of view. It's difficult to make it more complicated. Once you intersect with the generalization, complicated. Once we start thinking about, let's say, I don't know, memory limitations, complicated because you have lots of control variables. Once you start thinking about the model is so big it doesn't fit onto a single computer, then you have to have model parallelism or some kind of pipeline thing or whatever. And then there's communication there too. And here we're not bothered by that at all. So things in the real world are much, much more complicated. These are some abstractions which should be maybe some kind of, I don't know, guides, limitations, inspirations for what to do in practice. Yeah, so this gap will be there between what is being used in practice and what we understand in theory. But my hope is the more we understand in theory, the more we can trust in the practical systems, because if you stand on something that reaches higher, then you can build on it and reach higher. I mean, that's how I think of it. And the gap should always remain constant because practitioners are very smart and they can build on whatever is understood. And if the theoreticians build bigger foundations, then this raises everything up. But we'll never have complete explanation of everything. I'd be worried if we had. That would just mean that there's no job for many people, right? This is never going to happen. Okay, thank you.
All right. right, so we have a short break, and then we have our last talk of the day at 3:30.
It works.